In this video, I'm going to discuss the galvanic cells or explain how to use oxidation-reduction reactions to generate electricity. Let's say I have two beakers here. First, I have one beaker, and inside this beaker, I put solution of zinc sulfate. So it means inside this solution, I have ions of Zn2 plus aqueous and SO4 2 minus aqueous. So I put Zn2 plus here and SO4 2 minus here. Then I put a piece of zinc metal inside that. And I name this one electrode. So this one is zinc. I will see what's happening inside this container. When I look at this, I can't see anything, but actually there is something dynamic here. Always Zn solid, that is the electrode, becomes Zn2 plus aqueous and plus 2 electrons. So Zn dissolves and gives Zn2 plus and 2 electrons. And on the other hand, Zn2 plus from solution gets electron and becomes Zn. So the reverse reaction also is happening. But because the rate of forward and backward reactions are equal, so we can't see anything, but it's happening all the time. And right now, let's say that I have other container. This one again, I have one beaker, and inside this beaker, I put a solution of copper sulfate. So I have ions of Cu2 plus and SO4 2 minus. Then I put one electrode of copper inside. So this one is copper. And electrodes should be inside the solution. Just we name this metal that is conductor of electricity, electron. And let's see what's happening inside this solution. So I write down here, again, Cu solid becomes Cu2 plus aqueous plus 2 electrons. And on the other hand, Cu2 plus from solution, because we have Cu2 plus here, and again, SO4 2 minus here. Cu2 plus from solution gains electron and becomes Cu. Again, the rate of forward and backward reactions are equal, so we can't see anything. Right now, let's connect these two using a piece of wire. So we have separate container. Right now, just I want to connect these two using a piece of wire. And just to see what's happening here, I want to put a voltmeter here. When I connect this container, right now, there's a competition. If I want to talk about losing electron, right now I have zinc to lose electron and copper to lose electron because they are not separate anymore. They are they are attached to each other. So between zinc and Cu, zinc is more reactive than copper. What does it mean? Because they are metal, and when we talk about reactivity of metals, it's about losing electrons. It means zinc can lose electron much easier than copper. So in this case, between zinc and copper, zinc is the winner. Zinc can lose electron. So zinc loses, and because they are attached to each other, right now I have zinc losing electron. Let's say I have zinc 2 plus here. It dissolves here, it makes zinc 2 plus, and electrons are on the electron. Right now, I have this electron and they are attached to each other. Zinc 2 plus is one option to come and gain this electron again, or the electrons can travel all the way to this side and Cu2 plus gaining the electrons. Let's see between Cu2 plus and Zn2 plus, which one can get electron. If it's easier for Zn to lose electron, so it means between Cu2 plus and Zn2 plus, Cu2 plus can gain electron. For gaining electrons, Cu2 plus is the winner. So when this Zn loses electron in here, right now we have two options for gaining electrons, Zn2 plus and Cu2 plus. But Cu2 plus is winner, so electrons travel all the way to other side, and Cu2 plus here can gain this electron. So something that happens actually, Cu2 plus aqueous gains electrons, and gives Cus. And what's happening other side? Other side we have Zns giving us Zn2 plus aqueous plus 2 electrons. So if I look at this equation right now, because electrons from this system going out to other container, so it means this reaction is one way, is no longer two ways. So this reaction happening here. And in this container, because Cu2 plus gaining electron from other container, so it means the reaction that's happening actually is this one. So this reaction is happening, and this reaction doesn't happen any longer, but I wrote the reaction anyway here. So when you look at this, you can see the needle of your voltmeter moves and quickly it comes back to its original place. So it means that you generated electricity for less than 1 second. But how it's possible? Why it happened? Let's look at these containers closely. Look, if we look at this, at the beginning, the solution here was neutral. And the solution here also was neutral. Why? Because if Zn lost 2 electrons and becomes Zn2 plus, on the other hand, Zn2 plus gain that 2 electrons and becomes Zn. And because the rate of these two reactions were equal, the solution stayed neutral. The same story for this side. When we connect these two containers, electrons start moving from left side to right side. So as a result, the reaction that's happening in this container is this. So as a result, the number of Zn2 plus in this container, the left side, increases. So it means when the number of Zn2 plus increases here, so this container, the solution here becomes positive. On the other hand, because this side gaining electron and Cu2 plus plus 2 electron becomes Cu, the number of positive ion drops in this side. As a result, we have more negative ions here. So this container, the solution in this container becomes negative. So as a result, if this solution is positive, it doesn't want to lose any electron, because a positive solution doesn't lose electron. And if this solution is negative, it doesn't want to gain electron anymore. As a result, just you have that voltage for less than 1 second, and then it drops to 0. If we want to generate electricity, we need to fix this problem. It means we need to keep this solution, these two solutions, neutral. But how can we do it? For doing that, I want to use something to connect these two containers. So I use something that I name it a bridge. And this bridge is something like filter paper that you soak it in a salt solution. For example, let's say I have filter paper and I soak that in solution of KNO3, potassium nitrate. So right now here I have K plus and NO3 minus. I soak this one in solution of KNO3, so right now it has K plus ion and NO3 minus ion. Because of that, I name it salt bridge. It has salt and it's like a bridge that connects two containers. Right now, let's see what's happening here. If this solution is positive and we want to make it neutral, so NO3 minus from salt bridge needs to travel into this solution. And Zn2 plus from solution needs to travel into the salt bridge. And if this side is negative, right now, K plus from salt bridge needs to travel inside the solution. And SO4 2 minus from solution can travel inside the salt bridge. This movement of ions make both solution neutral. And also, by doing that, actually we have a closed circuit. Electrons moving here from left side to right side, and inside the solution, actually movement of ions conduct electricity. And you know, for conduction of electricity, we need a closed circuit. So right now we have a closed circuit here. So, and as a result, you generate electricity. To calculate the amount of electricity that is generated, we need to use some formula that I will discuss it in my next video. But also you need to know, right now this container, Zn losing electron, so it's oxidation half equation. And this container, that oxidation reaction happening there, this electrode of that, we name it anode. And other side, you see copper 2 plus gains electron. It means it's reduced. Reduction half equation happening in this side. So this electron, that reduction happens there, we name it cathode. So we have two electrode, anode and cathode, and also this one is cathode reaction or half equation, and this one is anode half equation. I hope you found this video helpful. If you would like to learn about how to calculate the amount of voltage produced by different cells, please watch my next video and please subscribe. Thank you for watching.